Good morning, class. Today we're going to be adding on to our knowledge about energy waves. In doing this, we're going to be reviewing some of the information that you learned in Part 2 notes. We will be calculating the speed of waves, and as you can see, the formula is the wavelength times the frequency. So just as a little reminder, I'm going to try to draw a wave on here. Say the wave starts here. Here I'm drawing the rest line where the medium would be if there is no disturbance or energy wave moving through it. And we have an energy wave that looks something like that. So, to remind you, the wavelength is the distance, so it is a measurement, usually in centimeters, from one area on the wave to the same exact area further on the wave. So here it's crossing the rest line. So again, when it's crossing the rest line and moving up towards the crest area, that would represent a wavelength. So this distance I would measure in a straight line, of course, and that would be one wavelength. Now, you could also find the wavelength by measuring from crest to crest or from trough to trough, okay? But here I can see that I have a wavelength, and we're just going to make up a distance of, let's say, 3 centimeters. Okay? And I have a total of 2 wavelengths, 2 and about a fourth. So we're going to say that there are 2.25 waves in a second of time, and we're going to pretend that in the drawing that I drew is equal to 1 second of time. So looking back at the formula, we know the wavelength is then 3 centimeters, and we know the frequency in 1 second of time is 2.25 hertz. And so all we do to figure the speed out is multiply those together. So it's important for you to know that there are several things that affect the speed of a wave, and that some of them are having to do with the actual wave itself, and some of them are having to do with the medium that the wave is traveling through. So if it has to do with the medium, there are 3 things that affect the wave speed, and that's the temperature, density, and elasticity of the wave. Now, if you remember from ocean currents and atmospheric currents, density and temperature are related. So when we're talking about a medium, if the temperature is higher, then the density is going to be lower. And if the temperature is lower, then the density will be higher. There is that negative correlation there. And also, the more dense a material is, the faster the mechanical wave will travel through it, but the slower the electromagnetic energy will travel through it. So it's important to remember that electromagnetic wave only propagates energy through a transverse wave, and it does not need a medium to travel through. So the more dense the medium is that it travels through, it actually slows down the movement of the electromagnetic wave. Now, for mechanical energy wave, it has to have a medium to propagate the energy, transfer the energy, and so it actually transfers energy more quickly if there is a denser medium, because the particles are very close together for it to move that energy wave. Elasticity, I don't know if you've heard of this word before or not, so we're just going to review it. Elasticity, the definition is the ability of a medium to return to its original shape after it has been disturbed. So the more elastic an energy wave is, the more the faster the wave can travel through it. So if the medium gets disturbed and it goes back real quick to its regular rest position, then the faster the energy wave will travel. So here we're looking at 2 different energy waves. I would like you to compare the energy waves and try to look at the 3 questions on the screen and try to figure out the answers. Which one is transferring the most energy? And remember what causes or what we look at to figure out the energy? Think about that for a second. The answer is amplitude. So when you look at both of these, if I'm comparing the amplitude, which is the distance from the crest to the rest, or the distance from the rest to the trough, these look pretty similar in height. And so therefore, they would each be carrying the same amount of energy. A lot of people would tend to say that this one actually does carry more energy because the frequency is higher, but that is not true. So we kind of answered the second question as well here, which one has the greatest frequency? Frequency is the amount of wavelengths within 1 second at a time. And if you look down here at the bottom of each diagram, it shows you that time is measured in seconds, and here's a 1, and here's a 1, so it's showing you 1 second at a time. And when we measure the wavelength in 1 second at a time, it is measured in hertz. So here we have only one wavelength from here to here in 1 second at a time, so this would be 1 hertz. But over here, we have 1, 2, 3, 4, 5 hertz. So this one has the highest frequency. Moving on to the last question, what are their speeds? Well, this is when we take wavelength times frequency. So take a second and see if you can figure out the speed of the first wave. All right, so let's see how you did. We said that there was one wave and it's showing a distance of 1 meter. So that is the wavelength, and there is only 1 hertz because there was one wave in that second. So your answer would be 1 meter per hertz. Next, let's do the second one. Go ahead and take a second and figure out what the speed will be on this one. All right, this time we have a wavelength of 0.5 meters, and we're multiplying it by the number of wavelengths in 1 second, which we said was 5 hertz. So when you multiply that, you get 2.5 meters per hertz. I apologize for the sloppy writing. All right, so compare these waves below. It's the same 3 questions. I'll give you a few seconds to figure out. For the first question, which one is transferring the most energy? The amplitude on this wave is much greater than the amplitude on this one. So for number 1, this wave would be carrying the most energy. For the second question, which one has the greatest frequency? Well, let's check it out. We've got 1 wave, 2 waves, 3 waves, 4. So we've got 4 hertz over here. And we've got 1, 2, 3, 4 hertz over here. So even though the one on the left is carrying more energy, they both have the same frequency. And then what are their speeds? Well, their speeds, the distance between crest to crest, which is 1 wavelength as well, is 1 centimeter for both. So each one of them has a speed of 4 centimeters per second. Okay. Next, here are some word problems. So you're going to solve these in the same way. It gives you information. Sometimes, and if you remember the formula, it is speed equals wavelength times frequency. So sometimes it's going to ask you to solve for speed, but other times it's going to ask you to solve for the wavelength or frequency. So make sure you plug in the numbers that the question gives you and solve for the missing or unknown variable. I will look at these when I check out your notes. Good luck.